773, our graduate seminars, first seminar of the year. It is my pleasure to introduce our speaker, Dr. Stephen Cummer. He is currently the William H. Younger Distinguished Professor of Electrical and Computer Engineering at Duke University. He received his PhD in Electrical Engineering from Stanford University and was a National Research Council postdoctoral scholar at NASA Goddard Space Flight Center. Dr. Cummer has written or co-authored more than 290 papers and is a fellow of both the IEEE and the American Geophysical Union. He's also a clever, highly cited researcher, and he received the Presidential Early Career Award for Scientists and Engineers. Dr. Cummer and his group have done some seminal work in electromagnetic and acoustic metamaterials. You'll learn today what metamaterials are. If you ever need a refresher, there is a very popular 5-minute video on YouTube by Professor Cummer that I think has almost 200,000 views. So that could be always a refresher. His current research area interests span a variety of theoretical and experimental topics in engineering materials and metamaterials for controlling acoustic and electromagnetic wave propagation, and also in geophysical remote sensing as well. So, Dr. Cummer, thank you very much, and the floor is yours.
Thanks very much, Augie. Thanks, everyone. Delighted to be here after a little bit hiccup yesterday getting here, thanks to Delta Airlines operational decisions, but I made it. I see many of you in the audience are students, which is great because I have targeted my presentation to sort of be a little bit of an overview and more a taste of metamaterials and what you can do with it, rather than a deep dive into a specific technical area or two. And of course, like for all faculty, my presentation leans heavily on work done by present and former students and postdocs in my research group. A lot of the heaviest lifting in what I'm showing today is from 3 members who are actually now all tenure track professors: Bogdan Popa at Michigan, Terry Shen at Rowan University in New Jersey, and Junfei Lee, who literally just started a week ago at Purdue. All those guys are in mechanical engineering, even though I'm an electrical engineer by training. So let's just dive right in. Acoustic metamaterials, sound and vibration. So you all are mechanical engineers, which means you tend, I'm sure, to think about sound more than electrical engineers. So I think you already have some appreciation for the ways in which you interact with sound on a daily basis. There are unpleasant sounds that you would like to mitigate. I get a lot of emails doing research in this space from people who want acoustic metamaterials to help keep the crying babies next door from being so loud for them, et cetera, et cetera. So noise abatement is definitely a big thing that people would like better materials for. Obviously, ultrasound imaging, whether that is 3D fetal imaging or, for instance, here, non-destructive testing, trying to identify cracks in oil pipes, gas lines, ultrasound sensing of sturgeons, trying to figure out if they have enough caviar roe to be harvestable at that point. That's a sound-based application. If you look around in rooms, especially big ones that are recently designed, I don't see any in here, but a lot of times you'll see features that don't really look like they serve much of a purpose. And a lot of those are actually placed there for acoustic control of the environment so that the room does not reverberate too much and voices get muddy, things like that. And obviously, sonar is really the only way we can image anything under the ocean, because electromagnetic waves don't travel effectively through seawater unless it's ridiculously low frequency or blue-green lasers, both of which are challenging. And then in terms of applications of sound, those are ones I think you know. Here's one that maybe you don't know. Modern cell phones have typically at least 50 individual bandpass filters to slice out particular channels of all the different spectra that they listen to. And all of those filters are actually surface acoustic wave or bulk acoustic wave devices, little components. And if you pop open a cell phone you can actually see where those components are embedded. And again, there are a lot of them. And the reason that those devices are fundamentally acoustic and not circuit-based or electromagnetic devices is that the elastic waves in those piezoelectric materials are about 100,000 times shorter in wavelength than the corresponding electromagnetic waves. So if you wanted to make comparable filters out of circuit elements or electromagnetic structures, each one would be something like this big, on the order of a wavelength or a significant fraction of a wavelength. And obviously that's not going to work 50 of those in your cell phone. And so it's super interesting to me that the solution to this is actually to take the RF energy, convert it into an elastic wave, do the filtering in the elastic wave domain, and then bring it back out as an electrical signal. So acoustics really is everywhere, even if you are not always aware of it. But then in terms of the tools available to all of us for materials for controlling sound, there's just not a whole lot of them out there. And the same is true in electromagnetics. Dielectrics, conductors, glass for optics, it kind of all stops there, and it's all about shaping those materials and deploying them correctly. But it sure would be nice, given all of the applications for controlling acoustic waves, if we had access to a larger range of material properties than just simple fibrous materials or solid materials. And so that's where the idea of metamaterials enters. Metamaterial is a word that doesn't really mean all that much intrinsically by itself, but it is a great word because it sounds so good. It was actually coined very early on in metamaterials research around 2000 by a researcher at UT Austin who was involved in early RF metamaterials, is no longer involved in that space. But he came up with the perfect word, and metamaterial is that perfect word. The definition of metamaterials has, I think, morphed a little bit over the years. In the very beginning, it was all about engineered materials with properties that you could not find in natural materials. For instance, a negative refractive index, which I will talk about very briefly. But the whole idea got broader and broader, and then people started to expand that definition to just encompass materials or some kind of engineered material that had properties beyond the components that you put into it, which I think is a good definition. It got even broader then, and people started talking about material properties on demand, that you can just dial in what material properties you'd like to have. I think that's a good one. I think the definition that I like the most right now is that it's simply an engineered structured material that uses that structure, and the structure is usually ordered, but it doesn't have to be. Ordered structure is just much easier to design and typically much easier to fabricate. But it's that engineered material that uses the structure to control transport of something from one point to another in the material, often some type of wave, electromagnetic, elastic, acoustic, but sometimes not necessarily something that's wave like heat transfer. So that's an intentionally broad definition that I think encompasses most of what people are doing in metamaterials now. Sometimes you'd like a material defined in terms of its intrinsic or effective properties, like how dense is it, how stiff is it, and if those are properties you can control, then you can control wave propagation through it. But sometimes you'd also like those materials to be defined not necessarily in terms of their intrinsic properties, but instead just what do they do to the wave, like an input-output relationship that's not always so well defined in terms of intrinsic properties. And that definition at the top sort of encompasses both of those. Okay, so this really was the very first, well, not technically the very first really big example of a metamaterial. That photograph literally is the device. And so this is an electromagnetic metamaterial designed for controlling RF waves. And it's obviously structured. The size of those squares that you see there is maybe around 1 centimeter. So it's very macroscopic in scale. And what this material was designed to do was have a negative refractive index. And the internal structure here in that picture is designed to deliver that. What you see is are sort of vertical wires that go through that. And that's designed to interact with the electric field in an electromagnetic wave and deliver a charge distribution that creates a dipole moment opposite in direction to the electric field. And then those loop-like structures are designed to do the same thing for the magnetic field. The magnetic field, I know you've all taken E&M physics at some point. You may not be doing it anymore, but you did take it. That magnetic field goes through those loops, induces a current, and creates its own secondary magnetic field. And the structure of those loops is designed to make sure that induced magnetic field is opposite in direction to the original one. And it turns out that you combine those two things so that those intrinsic properties are both negative. And what results, which was sort of a great surprise to everybody, except for the person who derived this back in the 60s, when it was just a theoretical idea, is that electromagnetic waves will still propagate through that medium, but they will refract the opposite way that they normally would. So illustrated here in the picture from that paper, this is sort of ordinary refraction, where through this prism, here's the surface normal to that outer edge. And what you've got is a wave coming in on one side of the normal, and then it refracts to the other side of the normal. That's normal refraction. But negative refraction is where the beam comes in on this side of the normal and then would exit on this side of the normal, like here. And that's precisely what they observed. And this was a great surprise to everybody. And there were lots of comments in the literature about how this was physically implausible and why it couldn't possibly be true. The dust settled after a couple years, and it really actually is true. And so this is a great example of just using that structure to control a couple of intrinsic properties of the material that define the material. And what emerges is a totally different kind of wave transport through that material. Another example, and this is in acoustics, this is sort of the counterpart from a design example. This is one where you're not trying to control the intrinsic properties, but instead the input-output relationship of the structure. It's a little bit hard to tell what that picture is, but it's thin circular latex membranes that are designed to interact with an incoming sound wave and vibrate. And then on each one of those membranes is 2 half-moon structures, 2 semicircles, that are sort of precisely placed in order to create resonant frequencies for those membranes that concentrate a lot of the deformation of the membrane at the edges where those thin metal semicircles are placed. And so that way, when the incoming acoustic wave interacts with those membranes, it creates a lot of energy dissipation at those points and attenuates significantly the incoming sound. So what gets transmitted through this thin membrane layer is highly attenuated sound at low frequencies, which is very difficult to attenuate by other means with natural materials. And so this, I think, is a good example of that input-output relationship, where you simply want a building block that when a wave comes in, you load as much of that incoming wave energy as possible into the vibrating structure and then dissipate it in that structure so that minimum sound is transmitted through. So, but another good example of metamaterial in that it is structure controlling wave transport through it. So just a few words to give you a taste of how this metamaterial design process can happen. In particular, I'm focusing this example on that first approach, where what you're trying to do is control or design the effective material properties of this structure in order to create a composite that acts like a continuous material with certain properties. So, and if what you want to do is control acoustic waves, for example, then everything is kind of driven by reflection and transmission at interfaces. And that reflection and transmission is driven largely by two properties of the material for acoustic waves and fluid: the mass density and bulk modulus or compressibility of that. If you know those two things, then you know how an acoustic wave will interact with a chunk of that material, what reflects and what transmits. But suppose instead of a continuous material on the left, you can, as on the right, you can create some kind of composite structure, and you can then interrogate that and simulate, for example, an acoustic wave interacting with that structure, and determine what's reflected and determine what's transmitted. And interestingly, what happens is that you have exactly the same number of free parameters in reflection and transmission as you do in those effective material properties. And you can show that if you know what that reflection coefficient and the transmission coefficient is, which are generally complex, then you can also determine exactly how that composite material behaves in terms of an effective mass density or bulk modulus, in the sense that you could replace the continuous material on the left with the composite material on the right, or for instance, put those two in a black box and say you can interrogate these however you'd like with acoustic waves, but you can't open the box and tell me which one you have. You can't tell which one you have because they behave exactly the same way. And that doesn't always work for composite structures. When it generally does work is when the wavelength of the wave in question is larger significantly than the internal structure of that composite. Because if you think about it, even a real continuum fluid is not a continuum fluid. It's got lots of discrete components that are really, really small and much, much smaller than an acoustic wavelength. And on the right-hand side, you're just mimicking the way nature works, but with your design structure. And as long as the wavelength is short, then the wave is kind of getting smeared over so much of that structure that it's unaware of the internal structure, just aware of how everything interacts in the bulk. And we did some early experiments long ago to convince ourselves that this actually worked well, and it does. So this is an example of reflection and transmission of acoustic waves from a very simple structure composed of solid inclusions that are rectangular in shape. And that does create an anisotropy in this problem, because waves traveling in what's called the x direction there, that's not the same for waves traveling in the y direction. And so you take that sample, and in simulation or experiment, you'll get the same answer. You measure the reflection coefficient for normally incident waves coming this way and for coming this way, and measure transmission. And then under those two orientations, take those reflection and transmission coefficients versus frequency and determine what the effective mass density is and the effective bulk modulus is. And what you find is that in the long wavelength limit, so to the right of these plots where the wavelength is many unit cells, those numbers become basically constant as a function of wavelength. And bulk modulus turns out to be the same in both directions, which is great because that's a scalar property and should be the same in that limit if this is really a fluid. And what you end up with is a mass density that is different in the two directions. That the wave sees this material as a denser material if it's trying to propagate in the x direction with the smaller holes, and a less dense, but still denser than air material if it's trying to propagate in the y direction. So we sort of validated that picture of the long wavelength limit. This structure really behaves like a fluid, but we've also got a property that we don't normally get out of fluids like air and water, which is that the mass density is different for motion in the wave in two different directions. which is obviously not, and it's not the physical property, but if you grab a piece of water, an ice cube, let's say, let's just use a piece of water, I guess, and wiggle it this way and wiggle it this way, of course, it has the same mass density and it wiggles the same. But this composite fluid acts as though it's something that is easier to move in one direction based on its mass density and harder to move in the other direction. If you go through the literature, particularly for acoustic metamaterials, I mean, sound can interact with almost any kind of designed solid structure. And there are lots of examples of acoustic metamaterial structures that people have used that all just deliver different properties. Something as simple as a scatterer array of just like solid cylinders or spheres. If you're arranged in a lattice anisotropically, then you get this anisotropic effective mass density property out of that. Helmholtz resonators, the middle top, that was the first example of a material that exhibited a negative bulk modulus. So you have a wave traveling down a waveguide where there are a bunch of side cavities. And when you hit the resonant frequency of those side cavities, then you get a negative bulk modulus where when you effectively, what that means is if you grab onto the chunk of material and you try and pull it apart, it doesn't expand, it actually contracts when you try to pull it apart, and it expands when you try to push it together. Which is kind of cool. Yeah, but it really, where that emerges from is the interaction of the wave with the resonant mode in these side cavities that enables the air to be pushing back the opposite direction because it's resonating inside that structure. It's kind of the same thing as if you just have a mass on a rubber band and do this like paddle ball. Like when you're at resonance in that case, you're actually pulling your hand back at the moment the ball is actually moving away from you, and then you're pushing in and it's moving towards you, and then you're pulling away and it's moving away from you. It's the same kind of effect. Perforated plates, an infinity of examples. Soda cans, people have done imaging experiments using the intrinsic resonant frequency of soda cans, which are actually pretty good and pretty repeatable Helmholtz resonators. And on water side or non-air-based things, lots of individual structures that you can put inside something like PDMS or water, any kind of polymer. Air bubbles are actually a great example of in water or a polymer of a structure that interacts very strongly with sound and can give you some fairly remarkable properties. Like I said, the bubble suspension. Got ahead of myself. And I'll talk about the one on the right, the labyrinthine structures, in a second, because I have an example for that one. Okay, so hopefully I've successfully conveyed some of the higher level ideas of, acoustic interaction with structured materials and how we can use that to deliver. We design things on the small scale in order to deliver larger scale properties. And here are some design examples that I'll step through. I will talk about the pagoda on the left and the spirals on the bottom. I will not talk about the cheesecake on the right in this talk. Okay. So to the pagoda structure, but we have to start with the basics. This all goes back to that work that made a great splash when it emerged in 2006 on electromagnetic cloaking. And what material properties could you possibly cover an object with that would render it technically invisible from sort of all means of interrogation. And so this is something that's very different from, say, stealth aircraft, which are all about redirecting incident radar signals from one direction and spreading that in another way, or also absorbing that incident radar energy. That makes something invisible to monostatic radar, where you're launching the wave and receiving the backscatter in the same direction. But you could certainly see that object if you had a sensor in another direction to pick up that scattered energy. Or even if the object absorbs all radio waves, then you can see its shadow. The idea is for like truly perfect cloaking, one way to do that is to make it so that an incoming wave goes around the object, it does not interact with it, but then fills in the shadow region, and what comes out of the shadow region is exactly what would have been there without any object at all. And it's interesting that I'm going into some details that I don't have on these slides. That whole concept emerged in this paper, 2006, by John Pendry. And who, interestingly, it's one of those stories where he had actually solved this problem 10 years before and just not really interpreted it correctly. And in the context of metamaterials, he sort of revisited that and said, oh, actually, this means you can do this. And what that theory shows is that if you want to create a particular geometric operation on a wave field, like bending it or displacing it or twisting it, if you can define that geometric operation, if you can write that down as a coordinate transformation from one set of coordinates to another, then you just need to operate on that coordinate transformation, and it's really just the Jacobian that tells you what this is. And that Jacobian tells you the material properties that what I've tried to illustrate here of, here's what happens if you take this propagating wave beam and you displace it and bend it. So there's the coordinate transformation. What transformation optics and then transformation acoustics, which was reported a year later, tells you what materials you have to place inside the box to make the wave do exactly what you specified it should do under the coordinate transformation. And that's pretty remarkable. Cloaking remains, I think, the best application in that people have envisioned to use this. Part of its limitation is that it's really good at deforming waves in a finite region, but then leaving them unperturbed elsewhere, which is not always the way you want to operate on waves. But what emerges here in acoustics in particular, shown down here, sorry, I'm switching notation on bulk modulus from B, which I used previously, to lambda now. I used lambda in that 2007 pager. My bad. But what emerges is, okay, a bulk modulus that depends on the Jacobian of this transformation that remains a scalar. So it's a bulk modulus that maybe varies from position to position, so it's inhomogeneous, but it's still a bulk modulus. But what does emerge on the density side is now, instead of a scalar mass density, it's a matrix or second rank tensor. So now that effective mass density is anisotropic, which is normally hard, except for the fact that metamaterials has already shown us that relatively simple solid structures can deliver an effective anisotropic mass density. And so maybe we're actually in good shape here. And so the experimental example that my group we published in 2014, which is not yet 10 years old, so the statute of limitations is not yet up. I can still talk about this because it's only 9 years old, is hiding an object on a reflecting surface, as illustrated on the left, where normally if there's an object on the surface, and this is going to be sound interaction with that. If there's no object, then it's purely specular reflection. If there's an object sitting there, then there's scattering from that specular reflection. And so the sound field is different in those two cases. The idea is we're going to cover up that object with properly designed acoustic metamaterials so that outside this region, like out here, you can't distinguish the reflected acoustic fields from the flat surface with no object. There's multiple coordinate transformations that you could use for this sort of thing. And in fact, the one illustrated here is not the one we used here. what we're doing is creating a hole here where we can hide the object by pulling this point up and executing this coordinate transformation. And we're doing this this is sort of a 2D illustration, but we're actually doing this in 3 dimensions. So it's not too hard to write down what that coordinate transformation is and work out what those acoustic material properties are. And so what we're doing is engineering a material that fills this space up here. And the mass density tensor that comes out of this is non-diagonal in Cartesian coordinates, but it's purely real, and so you can diagonalize it. And so you just need to identify the principal axes, directions, and what those effective mass density values are. And it turns out that what we need for the particular geometry that we chose is a mass density in this direction, which is almost perpendicular, but not quite to this outer surface. That's a little bit less than 6 times the density of air. And the other two are pretty close to air, and an effective bulk modulus that is also pretty close to air. And so this is just a great example of, you can't go to Home Depot and buy a fluid that has those properties, but you can use this metamaterial idea to design a structure that mimics those properties well enough to work. And here's what was made. You guys may not remember the state of 3D printing in 2014. Many of you were probably, well, you all are young, let's just say that. Really, 3D printing was just emerging. If we were going to redo this experiment, we would absolutely 3D print this structure and it would be super easy. But that wasn't available to us. And so this was actually hand assembled by PhD student who works at Intel now, Lucian Ziganayanu, who is a very meticulous guy, and he did a great job, and this is the perfect job for him to do. And so what the structure is just perforated plates that give a high mass effective mass density when you're trying to travel through the plate itself, where the holes are, and the size of the holes dictates how high the effective mass density is in that direction. And then the orthogonal orientations are traveling mostly in the gap between the plates, giving us that slightly higher than air effective mass density. Fun fact, the first one of this samples that was built totally did not work. Took us like maybe 3 or 4 weeks to figure out why. And the answer was there was ambiguity on diameter versus radius of the holes. And so we had the wrong size holes. And it totally didn't work, which actually in retrospect was nice confirmation that you had to design it right, that this wasn't just something that magically worked under all circumstances. You had to get the structure designed properly to make this work. And we then did some experiments in an empty lab where we had a loudspeaker, so tile floor, that's our reflecting surface, some wooden blocks placed underneath this structure that scatter, and loudspeaker here sending a short pulse down, and then a microphone that we would scan from position to position over this 2-dimensional space, launching a separate pulse every time, recording things in a time synchronized way so that we can take the recorded pulse, sound pulse measured at every one of those positions, and then assemble it into a 2-dimensional movie of the sound field that's coming off of this. And this is what that movie looks like. So I want to stop it here. So that's obviously the incident sound pulse from the speaker that's just outside of that field of view shown. So these are really measurements. That's the pressure field of the acoustic wave that you see there. And so the samples under test are outside of the domain that's measured. So everything looks the same right now because nothing's had a chance to interact with any of the objects. The middle example is where we have that wooden block that is going to scatter. And the right case is where we have this cloaking pagoda on top of that wooden block. And let me go a little bit farther forward to a point where, great, you can definitely see what's happening here. So on the left, no object. That expanding spherical wave is now just still an expanding spherical wave. That's the specular reflection that you get from nothing on the floor. In the middle, we now have this wooden block that's kind of shaped like this. So you get very little scatter from the apex because there's no flat surface here, and you get stronger scatter off in the specular directions from the tilted sides of this. So the difference between the left and the right examples, that's your ability to detect that that object is there on the flat surface. But then on the right-hand side, that same object is there just with the cloaking shell on top. And aside from some near-field perturbations that disappear fairly quickly with distance, the left and the right examples are pretty much the same. We've restored that scattering hole in the upward direction. We've reduced the specular scatter on the left and right-hand sides. And even we have delayed the reflection inside on the right-hand side so that the reflection that comes back is in phase with the reflection where there was no object at all. And that was amazing. This worked so well, so well. And that's why we managed to squeak into Nature Materials with this one. I'm going to skip that for time. So that was a great triumph of the acoustic metamaterial design process. And so then it just became a question of what more do we want to try and do with this? And talking to different students in my group, they get motivated for different things. The student who did this work, Abel Chier, was interested in the holography problem. And so you can project a complicated sound field with many transducers if you want, but you could also project a complicated sound field with a structure that patterns the sound field and just a single speaker. And so that's the idea, is we're going to come up with acoustic structure that's transmissive, but controls the transmission phase in order to take the smooth wavefront from a single speaker and make it into a complicated wavefront, so that then a certain distance away, we get a very complicated spatial distribution of sound. And so our building block for this is really more a good example of the input-output acoustic metamaterial relationship. So this is those labyrinthine or coiled up cells, and you can see along the top sample there that every one of these is coiled up a little bit differently. The more coiling means more time delay for the acoustic wave to travel through it, and so a greater phase change at a fixed frequency. And so the idea is, so these were designed so that we could capture a full 180 degrees of phase change, from 0 to 180 degrees of phase change with each one of these, so that if we stack two of them together, we have a full 360 degrees that's discretized a little bit. That turns out not to be important.
Steve, what's the direction of the propagation of the sound wave?
Yeah, it is this way.
Okay.
So that the acoustic wave has to travel along that meandering coiled up space. And so these samples are then reoriented this way and stacked up into a Lego style structure. So, and the acoustic wave will travel through this that way. You would think that we would have coordinated color with the particular sample, but we were using somebody else's 3D printer that had a bunch of random filament in it. So we couldn't do that. It was a little difficult to keep track of what building block was which. And so then the problem became a design problem of, if we want to project a certain sound field, what phase perturbations do we need in that hologram plane? Again, I mentioned that the student who led this work was Abel Chier, so he chose the letter A for the output spatial distribution of the acoustic amplitude that he wanted from this hologram. It's a pretty easy iterative design process to use this GSW algorithm to work out what phase changes you need in your hologram in order to take the incident sound field and turn it into the amplitude distribution you want at the other end. And so that phase distribution is that middle plot on the bottom there. And so you control that phase, And then I think it's a couple meters, you'll see on the next slide, a couple meters away from the output of that phase distribution, this amplitude distribution should emerge. Right, 1.5 meters. So the setup in an anechoic chamber provided by our colleagues at NC State, which was great. Again, scanning the sound field in this image plane to hopefully see an amplitude distribution that looks like the letter A. And, you know, we rotated our heads like there's just no way you can turn that into an A. I know I'm exposing a lot of our failures, but it's important, I think, for students to understand that things go south. This problem turned out to be an issue of sign convention in the time harmonic e to the minus j omega t or e to the plus j omega t between us and our NC State colleagues. Which took us about a month to sort out, but it turns out that the hologram was completely wrong and we needed to invert the phases because we had used different conventions on our two sides. So once we sorted that out, back to the drawing board, and now we got something. It's not the world's most beautiful A, but it is arguably an A, and scientific report said, okay, that's an A, you win, you can publish. Since this work, other groups have done like much better examples, more sophisticated, way more resolution. And if we were redoing this, we could do so much better. I know, but like, it worked all right. Okay, and then the last example that I want to talk about, this is more recent work. Where again, we're using structure to control acoustic propagation, but now we're actually trying to work towards doing something arguably useful. And this is in collaboration with my colleague in mechanical engineering at Duke, Tony Wong, who is among the world leaders in acoustic tweezers. And the idea here is that you can use the radiation force that comes from an acoustic wave, that does the scattering from a particle inside a homogeneous fluid. That scattering results in a net force on the object. It can be pretty small, but it's non-zero. And so if you sculpt the acoustic field just right, you can trap particles in locations and then move them as you change the acoustic field. And there are a lot of potential applications for this, a lot of in the biomedical space, where you'd like to be able to hold on to cells, for example, without physically contact them and bring them together, assemble them, hold them in place, move them apart, transport them from point A to point B. And it works great, but it all depends on the complexity of the sound field that you can generate. A lot of the work uses a pretty simple set of transducers on the outer edge of the chamber that's holding the particles. For example, in this lower right figure, you can see a bunch of cells that are trapped on a grid. Not every point is filled with a cell, but if you look at all of those and see how they're lining up, what there are 4 transducers on the sides of the square, creating a standing wave in both dimensions. And so there are maxima and minima of the acoustic field along that grid shape, and the cells are either attracted to the maxima or the minima, depending on their acoustic contrast, which depends on their internal properties. But if you can control the fields in a more complicated way, then you can create more complicated trapping patterns. And so the ideas that were out there, what you really like to do in order to create a more complicated acoustic field, you need to be able to put some structure closer to where you're trapping those particles in order to create that more complicated field. There's a limit to how complicated the fields can be away from a transducer. It's so much better if you can put objects nearby. And there are a few examples of that in the literature. For example, on the left is an example from Tony Wong's group where and this is a good one to illustrate the idea. There's some physical structure inside this chamber, and cells are pumped between these two walls, and acoustic waves are launched by those four transducers to nudge them onto particular sides of that traveling tube in order to sort the cells. But the problem with that is that when you have these physical boundaries there, the cells tend to clog up and it's really hard to unclog. There's a limit of throughput. And so our motivation in this was to say, maybe could we come up with some sort of virtual waveguide where the acoustic fields are confined to a narrow region, but without any physical boundaries, and come up with a structure to do that. And our idea for this was, we called it shadow structure, where the overall geometry shows that microfluidic chamber, that's the just water with the things particles we'd like to control, cells or whatever they are. And then underneath that, we have the physical structure that's going to control the acoustic wave properties inside the water. And so by controlling that shadow structure, we create acoustic waveguide channels inside the microfluidic chamber that don't have any boundaries in the chamber itself. And this was published in Science Advances, led by Junfei Li, the guy who's now at Purdue. And it's great work, and he came up with a whole bunch of different kinds of shadow structures that we could use, shown in the lower right, where we can create different shapes to waveguide fields that maybe have a maximum in the middle to trap negative acoustic contrast material particles, or a field minimum in the middle of the waveguide to trap and transport positive acoustic contrast. There's lots of things you can do with this. And it's a relatively uncomplicated structure that you need to build. Just PDMS based and things shaped appropriately with air as a very high contrast. And yeah, and it works pretty well. So this movie on the upper right, you can see where, so this boundary and this boundary are the edges of that shadow waveguide, because you can see through the whole thing, it's PDMS and water. And so what we've got is an acoustic wave field that is confined to being propagated along this, even though there's no physical waveguide in the chamber. And when you turn the sound on, all these little dots are the particles that will be trapped. You see them all coalesce onto the maxima of this standing wave field that we're generating by having two transducers on the end. So these trapping points are these field maxima. Then when we change the relative phase of these two transducers, we can move the positions continuously of where the maxima and minima are, and that drags the particles along. And similarly, we can create different kinds of structures that trap particles along acoustic minima, which turned out to our surprise be lining things up in a very thin line, because minima are much narrower than maxima. And we also, that's not a movie, sorry, we can also trap along a curved path. So this is an example of something you definitely cannot do with just transducers and no structure. Create a path that will trap the particles and transport them along something curved. And then Junfei had the great idea of, right, we can use phase to shift them left and right, but what if we actually detune the two transducers? So this frequency is just a little bit different than this frequency. Then you actually have a continuous phase change along the waveguide, and you end up with a very slowly propagating transporting standing wave structure. And that's analogous to a quantum mechanical phenomenon called the Fowlis pump. Fowlis won the Nobel Prize a handful of years ago, I think. 2016. 2016, yep. And do I really want to illustrate? Yeah, here's the movie we get from that. Where now when we've trapped these particles and then we detune one side, they just march along the channel that we've defined via this shadow structure in an otherwise unbounded trapping chamber. And so there's nothing for them to get stuck on. And we can make them do whatever we would like them to do. So trying to figure out now what we can actually do that's useful with that. Okay, just to close it all off. Metamaterials, it's just exploiting structure to create functionality for some kind of transport or wave control. I think it's reached the point where like there are enough examples in the literature that you can go to find some guidance on the kinds of things that can be done. And so if you have an application in mind where you'd like to be able to shape a wave or make it do something in particular, there's no like textbook that'll tell you exactly how to do that, but there are a lot of examples that will, I think, guide you towards how to do it. And not surprisingly, the more complicated the structure, the more complicated the control and functionality that you can deliver. And there's really two challenges in that I see. One is fabricating the structure. The more complicated your fabrication and the larger the ratio between the smallest, the overall build size of the sample you can make and then the smallest feature inside you can control, the larger you can make that ratio, the better. And 3D fabrication is getting better and better. I think we're still a little bit limited that you can't 3D print something that's this big that has 10 micron internal structure that's like completely controlled. Yeah, that would be a 10 to the 5 ratio. And we're really more at the 10 to the 2, maybe 10 to the 3. But 3D printing is going to get better. Maybe some kind of bottom-up self-assembly is the way to solve that particular problem. But I feel like it will be solved. And then the other challenge is designing the structure to do what you want. How do you solve the inverse problem of saying this is the structure that will perturb the waves or control the waves the way I want to? And that's also a challenge if the structure itself is really complex, because then you just have to do a lot of simulations that are very time consuming in order to come out with the one that you want. But computational power is ever increasing. So if you can't solve it now, hopefully in a year you can. And maybe there's even some promise for AI machine learning approaches for efficiently exploring that design space. People are just starting to dabble in that. I think I have yet to see an example of a design that emerges from that approach that you couldn't have got via other means, but I bet something like that is coming soon. And so, you know, the closing thought is that metamaterials, it's important to realize, cannot deliver everything you might want. We're still subject to the laws of physics that inhibit us from doing everything. But if you're thoughtful about what you're interested in, there are some pretty interesting applications that emerge that are definitely feasible and doable right now. So with that, thanks for your time. Happy to take any questions.
So let's open the floor for questions. Speaker?
I know one.
Yeah, go.
I think what I understood correctly from, okay, to ensure to reach some goals, you design the structure. But I think I'm not expert on this topic, but what I remember that in Tel Aviv University, there are some groups, they were working about designing, controlling metamaterials by external actuation to ensure some goals. I think you work on this because I think they were doing this by realizing these actuation signals with ILC service.
Yep. So right, that's a great point. Actually, I know it's.
I know you didn't mention about it, right?
I did not mention about it, but that's a great point. All the examples of structure that I showed are fixed, not dynamically controllable. For sure, if you can come up with an approach that enables you to dynamically control the properties of the structure in some way that you can either adapt what the structure does to the wave, or even better, close the loop on something and just say, I want this, and let it solve itself in a controlled sense, how to do that. That would be even better. It's for electromagnetics, it's relatively easy. For acoustics, I haven't seen anybody come up with a really good example of how to do that efficiently, because so much of this is based on like solid geometry, at least the examples I've shown, and it's really, nobody has a good solution that I'm aware of. If you know of it, please tell. Reconfigurable, reshapeable solid structures that like are not glacially slow and require enormous amounts of time to do that. But for sure, taking adaptive approaches where you can control some properties dynamically adds a whole other dimension to this that is really, really
Yeah,
useful.
because like in slide 20, like for clocking example, I mean, two pictures are quite similar reflection of the sea waves, but I think you mentioned about like some phase changes, and in control perspective, I think, of course, we don't know the exact mathematical model of the Metamaterials, and I think it's very difficult to model it somehow. But I mean, in control perspective, it's possible.
Yeah, and that's a great point. I've seen a few examples of that. It's not widely used yet, because I think of the limitation of the ability to dynamically control the structure.
Thank you.
And I think things get very interesting when the time scale for the control becomes fast enough.
Oh, comparable to the wave?
Yeah, then the physics becomes
that's
very
a-
beautiful.
Right,
Yeah.
that's a whole other thing. One, you can reconfigure things on timescales of seconds just to make your device do something different. But then whole new avenues of physics emerge when you can dynamically control the structure on the timescale of the period of the wave. And then you're really like controlling every piece of the wave, like the phase locally, yeah.
Yeah, Frank?
So I was wondering, you are talking about this acoustic contrast, so some particle goes to the maximum of the acoustic, and some go to the minimum. So what determines this? Maybe some they don't.
No, there is all right, I should know the formula off the top of my head, I don't, but there is a parameter called acoustic contrast that is a function of both the density and the bulk modulus of the small particle relative to the background fluid. And that just controls the overall scattering of the particle and tells you that number can be either positive or negative.
Yeah, I have two questions. So can you go back to the A slide? The slide with the A?
Oh, yeah. Somebody told me how to. I know there's a way to just enter the slide.
Oh, yeah, that's the one with the,
Oh, yeah, right,
yeah, the spiral structure.
like,
Yeah, if you can go back one or two slides, yeah, with the spiral structure.
Oh.
Yeah, this one.
yeah, okay.
So is there any, is there any physics to why the choice of this spiral structure? Is that crucial to the physics of this problem? Or it's just a matter of convenience of fabrication?
Well, no, I would say it is in the sense that what we've designed these metamaterial unit cells to do is to change the phase from input to output by a specific amount.
Yeah.
And the way we're doing that is with that coiling and the associated time delay. So the acoustic wave is not traveling through the solid structure, it's through the air gap in the interior of that.
I see.
And
So-
the more coiling we get.
So I can understand by the length of that spiral determines the resonant frequency.
I would say that the length of that spiral controls the time delay of the acoustic wave that as it travels through this structure.
Okay.
And then at a particular frequency, that time delay corresponds to a particular phase. So it's not, there's actually, and the way that the spiral is sort of continuously shaped, it's not just a square, but it's sort of horn-like, is designed to minimize reflection and maximize transmission. So we're trying to transmit as much possible acoustic energy through these structures as we can, just with varying phase shifts for different structures.
And yeah, thank you. And then you have this cloaking, right? I would guess maybe for acoustic, you don't have any issue with, say, dispersive effect. Like, is it achromatic? I would imagine it's naturally broadband.
The structure that we came up with, yes, is naturally broadband in the long wavelength limit.
Okay.
So if you go back, like our perforated plates, there is a periodicity to that structure, and also the spacing between plates in that layered pagoda-like structure.
Yeah.
And as long as we keep our wavelength longer than those spatial scales in the structure, then it works, which is.
So there is no such thing as dispersive effect in acoustic.
Well, I mean, you can design a structure to have a dispersive effect.
Okay.
For the transformation acoustics material properties that we're trying to realize, we don't want dispersion.
Okay.
So we intentionally use a metamaterial design that is not dispersive.
Okay. Thank you. Very nice.
Other questions? So I have one. So this I don't know what maybe the length scale here is,
I
but
should have put a finger in that. The distance of each one of those is maybe 2 centimeters.
2 centimeters. So 3D printers are getting better and better, and we're getting better at making structures smaller and smaller.
Yeah.
Something I'm curious about, there's still kind of the fluid that is participating in this wave transport. As you get smaller and smaller, how does the wave aspect of it now, do losses come into, and kind of, how do you expect this to scale to smaller and smaller sizes, and
Right.
how that might affect the property?
Yeah, so in air like this, you don't think of air as viscous, but it is. Viscosity is not very big, but it is. And if you try to force airflow in thinner and thinner channels, then the thermoacoustic boundary layer that forms along the edge starts increasing the drag and the losses. So scaling this up in frequency by a factor of 10, and so just scaling the particles down by a factor of 10, I think the losses would increase dramatically. So it's hard to do this kind of thing where you're forcing airflow in an acoustic wave, because that has velocity in the longitudinal direction, through really thin channels becomes problematic. In water is where the more successful small scale experiments have been done. And there, it's not so much using thin channels, but instead using shaped materials with water-like properties,
Very interesting.
like PDMS.
So by the way, for this structure, is it correct to think of this as a meta surface, because the sound wave is just propagating through one unit of the meta?
Well, it's actually propagating through two, but it is, the overall thickness of this is maybe 1/10 of a wavelength. So is that a metasurface? I think probably, but the boundary between what's a bulk metamaterial and what's a thin metasurface is murky. But this is more of a metasurface than it is of a metamaterial, because this is a thin layer that just sort of does one thing to the wave as it travels through. It doesn't bend it or redirect it, just takes input phase and creates a crinkly output phase.
Any other questions?
I have 9 questions. So how do you?
Those are the worst questions because they're usually very deep, but go ahead.
So how do you measure the reflection coefficients for transmission coefficient experiment? Because in some way, some objects, you have this scattering. And how do you measure how much is reflected, how much is transmitted?
Like experimentally. So that's actually something that there are standard test setups for acoustics, that you typically have a waveguide, often cylindrical in cross section, and a section in the middle where you have your sample. And you can either send a short pulse and then measure microphone standoff distance from the sample so that your incident and reflected waves are time separated and don't interfere with each other. Or probably a more accurate approach is you use something called the 4 microphone method, where your source in this tube is launching a single frequency wave. And so there's interference on the transmits, on the incident side from the incident wave and the reflected wave. But the 4 microphones plus your knowledge of the wavelength enables you to separate those two things. And the 4 independent measurements in that waveguide enable you to separate incident, reflected, and transmitted signals. And you get a full amplitude and phase of that. Call it impedance tube. And E&K is maybe the most well-known company that sells them. And they're so expensive. They must cost them like $200 to make, and the whole system is like $25K. It's unbelievable, the margins. Those guys.
Economies of scale, right?
Yeah, so they're kind of the only ones in the business who've solved some problem, so they're just minting money.
Go ahead.
On the particle transport slide, can you speed up the particles moving along with a stronger signal or like a higher frequency wave?
Well, when we're transporting them, so what dictates the speed of transport is the frequency difference between the 2 transducers on either side, because that dictates how fast the phase of the standing wave is changing. And so you can speed things up by changing the relative frequency of those, which is actually pretty appealing because that's a very easy change to control. Eventually, you start to run into drag related problems if you try to move the particles too quickly. If they're like sort of agglomerated like this, you kind of saw that in one of the movies, that they're trapped like this and you start to move them and then this whole body starts to like drag. But you can control the speed via frequency.
I have a question about the cloaking of what, so you have your kind of control experiment, there's this wooden pagoda, right? And you see its scattering profile, then you put the metamaterial pagoda on top. But in principle, anything else can be under, right? It doesn't have to be the wooden pagoda under, right?
It could be anything. Yeah, that's right. So there is a subtle point here that you're touching on, which is that
yeah, exactly there. Yeah.
that this boundary right here is actually needs to be a rigid boundary. And then obviously you can hide anything you want in this space because this rigid boundary prevents any direct acoustic interaction with an object under here. So the key thing is that this material property distribution here is what makes this bumpy surface, because now the reflecting surface is this flat, but this slope and this slope. It turns that triangle shape into the equivalent of a flat reflector.
So my question was, are there any near fields on that, along that red line that would actually go under in the white region, such that you might have to be careful how close you are bringing your cloaked object or not?
It depends whether you are doing this in air or water, I think. If you're doing it in air, then the contrast between any solid material and air is so high that there's very little acoustic transmission through an air-solid interface, even if it's pretty thin layer. If you're trying to hide submarines underwater, that's a whole other story, because it's not easy to make a fully reflective surface, because water and solids don't have such a high contrast. So in that case, you would need to be more careful about your design, and there could be that kind of interaction.
Any last questions for a speaker? Okay, well, let's give another round of applause. How do we listen to the system that we're using for the first time?
Right, first, nobody say anything embarrassing. Nope, yep, recording.
Looking for my phone. I can't go home because my phone is here.